So, partial fractions. Let's get straight on into it. Now, you'll remember from National 5, we learned how to transform these types of fractions into one big fraction. This time in Advanced Higher, we're going to learn how to transform these big quotients back into partial fractions. So the aims for this lesson, if you'll look to the right, is know how to turn large quotients into partial fractions. Very simple stuff. Let's get straight on into it. Pardon me. So, let's have a little chat about degrees. Not university ones just yet. That'll come in time. So, x squared minus 2x plus 3. The degree is just telling us what the highest power in a function is. So if we look at this function, x squared minus 2x plus 3, what is the highest power in this function? It's 2, sorry. So we say it has a degree of 2. And then if we look to the next one, I'll let you have a little go of this on your own. So we have 6x to the power of negative 2 plus 2x to the power of 15 plus 9x. So the highest power here is 15. So we have a degree of 15. Now let's have a little talk about rational functions. Bit of a fancy wording there. So px over qx, where px is a function as well as qx. Now, we were just talking about degrees of functions, and if the top part, the numerator of the fraction, has a greater degree than the degree of the denominator, which in this case is qx, we call it a proper rational function. And if the degree of the top part of the fraction, the numerator, has a degree less than or equal to the degree of the denominator, then we call it an improper fraction. So let's take a look at some examples. So here, we've got x squared plus 2x minus 1 divided by x cubed minus 3x plus 4. Is this an improper or proper rational function? Well, we've got a degree of 2 on the top, and we've got a degree of 3 on the bottom. If we look back to our rules, it follows this rule. So it is a proper rational function. Proper. Let's have a look at the next one. That's a very dodgy saying. I'll just change that. Stuff like that bugs me. That's better. That'll do. So we have x squared plus 2x minus 1 divided by x squared minus 4. So we've got a degree of 2 divided by a degree of 2. Well, let's have a look back at our little rules. Now, the improper rational functions, it's so easy to forget this, so please dig it into your memory. If the degree of the top part of the fraction is equal to the degree of the bottom part of the fraction, then it's an improper rational function. Right, do not forget it. If it's less than or equal to the bottom degree, it is improper. It's an improper rational function. So, following our rules, degree 2, it is improper. It's an improper rational function. Improper. Now, let's take a look on how to actually turn these big quotients into partial fractions. Pardon me. So we have something here divided by x plus a times x plus b. Now these are called linear factors because they're only to a degree of 1. That means that the highest power of x is 1. So it's very easy to split these apart. We just split them apart into their designated factors, which in this case is x plus a and x plus b. Let's take a look at a quick example. So we have down here 7x plus 1 divided by x squared plus x minus 6. So let's follow the rules. We factorize this part which is the denominator, and that factorizes into x minus 2 times by x plus 3. And following our rule from up here, we turn it into a over x minus 2, plus b over x plus 3. Now, what we do is we actually reunite the denominators into a common denominator, which is actually this part here. I'll highlight it in a different colour, which is this part here and here. So, it's just like using addition for normal fractions, just with a bit more algebra. So, how do we make them add together? Oh, excuse me. Well, we times this side by x plus 3, and we times this side by x minus 2. And that gives a common denominator of x minus 2 times by x plus 3. Now, you'll be thinking down here, well, where have the denominators of the fractions gone? The truth is, once we've got the same denominator on both sides of the equation, then they actually cancel out, so we don't have to actually look at them now. We're only interested in the top part of the fraction. Now, 7x plus 1 equals ax plus 3 plus bx minus 2. It's actually very easy to solve here. All we need to do is use knockout values. So we'll use negative 3 here. So negative 3 plus 3 equals 0. A times by 0 equals 0. So negative 3 minus 2, that gives negative 5, and then we rearrange all of these equations to get a value for b then, and then we replace the value for b back into the original equation here, and then we use a random x value in this case to solve for a, which we could use 1, and then we just do our simple equations again to get the answers. And then, once we've got the values for a and b, we implement them here. And then we've got our partial fractions, or I should say here, sorry. Now, for repeated linear factors. So say we have something over x plus a cubed. We do a over x plus a, plus b over x plus a squared, plus c over x plus a cubed. Now, it goes up to the degree of the original fraction. So if it was x plus a to the power of 4, we would go from a to d, and also it would be x plus a to x plus a to the power of 4. So let's take a look at an example. So 5x plus 18 divided by x plus 4 squared. Well, we split it up. We have a over x plus 4 plus b over x plus 4 squared. Now, what we do is we get a common denominator again, which is x plus 4 squared, which is what the left-hand side denominator always is. So we don't need to times anything on b, but we do need to times x plus 4 on a. That gives here, since the denominators cancel out, 5x plus 18 equals a x plus 4 squared plus b. Now we can use another knockout value, which is negative 4, right here. Those are our little dodgy arrows. So we use negative 4, we replace negative 4 in here with the x, we rearrange all of this to get b equals negative 2. And then what we do next is we replace negative 2 back into the equation, and the next part is we can use a simple value for x again, like 1, and rearrange that to find a, or we can multiply everything out in the brackets still in terms of x and a, but we have the value for b. And then we move everything we can to the left-hand side, and then we figure out what a equals. That's called realigning the coefficients. Time for the third type you'll face in advanced higher maths. So it's an irreducible quadratic. Bit of fancy wording there. Irreducible means it can't be factorized. Okay? So if it's something over an irreducible quadratic, we do x plus or ax plus b over the irreducible quadratic. So let's take an example. X minus 12 divided by x cubed plus 4x. Well, we can actually simplify it a bit. We can take out a common factor of x, and then that becomes x times by x squared plus 4. And we can actually split that up again into a linear factor this time, and also an irreducible quadratic. Now, what we do is a over x plus bx plus c. Now, it depends, the lettering depends on the order you put it in, okay? Now, we get a common denominator again. So that would be x times x squared plus 4. So a times all of that, we get this. Right? And so this time we can choose x equals 0 to find the value for a. So when we use that, these terms get knocked out. So 0 times by anything is 0. And then we get a equals negative 3 after rearranging everything. And then what we do after, we replace a back into the original equation, which is this equation, all of it. But we keep x the same this time, so we just keep it as x. And then we expand all of the brackets, and we move everything that doesn't have b or c in it to the left-hand side. And then it will be something like, I don't know, x squared plus 2x plus 1 equals bx squared plus cx. And then we can look on left-hand side and right-hand side to find out what the values for b and c are. That's called realigning the coefficients. So, there we go. I forgot I've written this actually. So we've realigned everything. So we've got the value for a. We replace a. So we've replaced a here. We expand everything here. And then we move what we can to the left-hand side. Or no, sorry. What else you can do is b minus 3x squared. That's b minus 3 is the coefficient of x squared. But there is no x squared on the left-hand side, so that means b minus 3 must equal 0, which means b must equal 3. And then we have cx on the right-hand side and x on the left-hand side, so c must equal 1. And then we've done it. We've got our partial fractions. Well done us. So, for a final note, you need practice at advanced higher, as I'm sure you'll know, because higher, that's kind of easy once you look back. But no, higher wasn't that difficult. It was more the quantity of work, which was a bit of a step up from National 5. But this year, it's difficult and a lot of work. So practice every single day at freeadvancedhighermaths.com. It is a brilliant site for studying. It has questions on every single topic and plenty of them as well. So thank you very much today for watching my video. Check out the YouTube channel later on. I'm uploading videos more frequently now that I'm getting more of the course available. So thank you very much, and I'll see you next time. Bye.